need a device for, yeah. There's the device. It makes me easier to answer hard questions now. Yeah, so I'm Alexeev from Georgia Tech, and I want to talk about the research we do on elastic swimmers, understanding hydrodynamics of elastic swimmers. So essentially the main topic of this talk will be hydrodynamics. And this work essentially is done by my graduate student who works in my group, Peter Ye. He's only second year undergraduate student, so we will see many parts that need to be completed yet. But okay, so essentially the motivation for us is we want to understand what happens with swimmers which are in a sense mimic of a fish, right? So fish, we know they are very efficient, they swim fast, they use very efficient modes of swimming, which this picture show different modes of the fish swimming that goes from essentially the differences in the way how wave propagates through the body of a fish, and this is faster swimmer goes up, so this is the faster, this is slow. So it is rather complicated process, and what we want to understand is what's the role of elasticity in this swimming and how we can use elasticity in order to maybe design an efficient swimmer. And elasticity gives us very interesting features. For example, we can think about some resonance oscillations, and there is some discussion in the literature if resonance is efficient for swimming, it's useful for swimming, if it gives any advantages for swimming. So in my talk today, I will be focusing on low Reynolds number hydrodynamics, which is around 100. Reynolds number is around 100, but it's of course huge compared to what we saw before when we saw some beautiful talks about bacterial commotion that swims in a Reynolds number which is almost 0. So this is huge jump, and the main difference between what we saw before and now is the addition of fluid inertia to the story. So we have a competition between three effects in the system, which are inertia of the fluid, viscosity of the fluid, and elasticity of the swimmer itself. Okay, so the goal is we want to understand the role of this elasticity, and the way for us to do this, we focus on the simplest possible model, at least that I would think is simplest possible. So essentially elastic plate, which is oscillated at the root, right? So this is the animation that shows this plate. So the red is essentially the elastic surface. We apply some oscillation at the root, and we want to see how this guy will swim, depending on the parameters of this plate. So we want it not just because we want to know how fish swim. There's growing interest to build some robots that can effectively swim underwater. I mean, I don't know what purposes you can think about for these robots, maybe spy for someone, but there's growing literature, and you can see these are few examples. These are more recent, this is less recent, this is a robot unit that designed at MIT. But if you can look at these designs, so you will see there are a bunch of different elements inside, including some joints, servo motors. So it is a really engineering device, so students like to build this kind of stuff, but it is very complicated. And if you want to build something relatively small, so probably it is not very efficient way to do this. But why you need these kinematics, I'm sorry, these elements, because essentially they want to try to copy the kinematic of a fish, right? So we saw this different mode of fish motion, so they want to introduce these different motors to be able to bend this body in the same fashion. So the question is, can we use maybe elasticity to give us the same result without using these very complicated elements? Okay, so there is indeed a different approach to build robotic fish, and this is essentially involved using so-called active materials. And this animation actually shows this fish, robotic fish, that swims through this aquarium, and it is driven by this elastic plate, which fluctuates, right? So this is so-called microfiber composite bimorph, and essentially it's a sandwich of some polymer, and it has two layers of piezoelectric material. When we apply voltage, it starts bending. That's it, right? It bends. It has relatively large amplitude of bending, relatively voltage, so very good advantages over the design I showed before. But the question is if we can make this swimmer or this material, or use this material to make a swimmer that swims efficiently. Actually, the reason for me to be interested in this specific material, because I have a collaborator that sits pretty much next to my office in Georgia Tech, and he's an expert in this material, and he told me this is the best one we can use, and I believe him. So in reality, there are some other materials. I looked at in the Google, so there are some other materials that can exhibit these properties, and to make some connection to liquid crystal, okay, it's hard to see here, to our liquid crystal workshop. There, for example, liquid crystal elastomers that can be actuated or responsive to light, and this is image, it's kind of blurry, that shows liquid crystal. It's essentially beam, cantilever beam, that its work was by Tim White from Air Force Lab. And when they eliminate it by laser, so it starts oscillating, and it's oscillating very fast, you can kind of see this blurry image. So it's essentially very fast oscillation. That's what we see, and the frequency is like 30 hertz. So it is maybe a nice replacement for this material. But again, what we see here, we see a material that is internally actuated, right? So it produces some internal forces that cause these shape changes, and we want to understand if this material can be useful for underwater propulsion. And essentially, my story will have two parts. In the first part, I will show you what happens if we have an elastic plate which we actuate. And the second part, which is kind of shorter, will show what happens to the story if we use a swimmer that essentially have this active material and can bend effectively. So it's kind of two extremes, essentially, of the same problem. In one side, we apply the force focused at the root. In the second side, we distribute the force over the entire swimmer. Okay, so we do it numerically. We use it. Our method is for fluid structure interactions, fully coupled method. So we calculate in 3 dimensions this elastic swimmer in viscous fluid. To solve our hydrodynamic flow, we use lattice-Boltzmann model. I will talk very briefly. Essentially, you can think about lattice-Boltzmann as a method when we have a set of fluid particles that propagate along a fixed in space lattice, right? They organize it such that they, in one time step, they propagate to next node, they collide, exchange momentum, and this way we can reproduce hydrodynamic behavior of a Newtonian fluid, right? I feel obligated to show at least one slide with equations. So here's the slide. So this is discrete Boltzmann equation that describe this process. The main component is essentially this post-collision operator, which tells us how these fluid particles that described by distribution function relax when they collide, right? We use a model they developed by Tony Ladd from University of Florida, and we have 2 relaxation parameters. One relax shear stresses, another relax volumetric stresses. But so equation is very simple. So the model computation is very efficient. And if we want to know the hydrodynamic properties of the system, we just take moments of the distribution function, and that's pretty much it, right? So it's very, very easy to do. We use a 3-dimensional model which has 19 directions. It's called D3Q19 if you want to look at the literature. Okay, so we have a second part of our fluid structure interaction model, which is so-called lattice spring model, or it's bond bending model. There are different names for it, but essentially what we have is we have a lattice of springs that connect point masses, very similar to what we saw in the talk today morning. We have regular lattice of triangles, and because we're talking about a very thin plate, we use two-dimensional lattice, right? So we have stretching springs and bending springs. So we have bending elasticity, which is essentially the important part for the model. We can calculate what's the bending modulus. We can calculate Poisson ratio for the system. The thing is that it matches very nicely linear theory. We can show it here. So we kind of have a model, simple model, which can reproduce elastic behavior of a cantilever. And to integrate the dynamics of the system, we just solve Newton's equation of motion using Verlet algorithm, the same we usually do with any molecular dynamic code. Okay. Sorry. So the main thing why we use actually lattice-Boltzmann for these problems, for this fluid structure interaction problem, because lattice-Boltzmann is very simple if we want to couple it with solid. And we use, this is the boundary condition we use, so it's essentially bounce back. If we have a fluid particle that cross surface of my swimmer, we just bounce it back. That's it. That's the whole boundary condition, and that provides no slip boundary condition on the surface. We have some procedure to exchange momentum between fluid and solid, so we have fully coupled system which conserve momentum. And we use actually interpolated bounce back that divided by this in this paper, and these give us second order accuracy sharp interface boundary conditions, very nice for our problem. We can show this is second order indeed if we play with spacing of the nodes. So, okay, so let me finally go to the problem we solve. So essentially this is, as I told you, a rectangular plate oscillated at the root. It is given some sinusoidal law. We fix the amplitude 0.1 length of the swimmer, and we use the characteristic velocity as frequency of the oscillations times length, and Reynolds number is this characteristic velocity times length divided by viscosity. It's a little bit strange Reynolds number for this problem, but the thing is we keep these parameters fixed through all the simulations, right? So that's why we define the Reynolds number this way, so we don't change it essentially. All other parameters we will change, right? So what are other parameters? Other parameters important for us is added mass. So it's essentially a ratio of the mass of the fluid that swimmer displays to mass of the swimmer itself, right? So the heavier the swimmer, the lower added mass we have, right? Because the density of the fluid will not change. Then the second critical parameter for us is reduced frequency, which is essentially frequency of the oscillation divided by the resonance frequency. And as I told you, the frequency of the oscillation, we fix it. So what we change is the resonance frequency. And resonance frequency is here. It's very important. It is frequency in water. It's not frequency in vacuum. So this frequency actually depends on Reynolds number, aspect ratio, added mass, and this is essentially frequency for a cantilever oscillating in water. There is a beautiful paper by Sutter that gives us the theory that help us to calculate this value in the limit of high aspect ratio beams, and we use it to calculate the reduced frequency. So we use a relatively large domain, which is like 16 length of the swimmer. So we tested it is not, it is periodical, right, in all directions, but we tested it's large enough so we don't have some interaction with the wake of the swimmer itself. And essentially we model a swimmer in an unbound fluid, and what we're interested is we want to understand what's the, how fast the swimmer will swim in free conditions. So there's no forces, it's untethered, it can swim as fast as it wants. We want to understand what happens to the swimmer in this story.
How is your oscillation? You have to apply an external force.
Well, yeah, we apply the force in the vertical direction, which is constant because it's total zero, right? It's periodical.
Right, but at any instant.
In any instant we have forces, of course. But on average, on a period, it's zero.
So you imagine in a model of a fish that force is being applied by the body of the fish, and somehow this
you can think about this a fin essentially, and then you have the fish flapping it or something like that. right? Or you have
What I'm getting at is
some
that this isn't the force dipole.
right. It's
monopole,
yeah,
which
yeah,
is
yes.
a bit artificial.
It is. Yes, yes, yes. It's the force is essentially. Well, we actually apply kinematics at the root. So we don't know what the force exactly because it changes, right? We apply the displacement at the root.
Yeah.
So see, it's yeah. But you're right. It's kind of monopole in this sense. But the thing is that over one period of oscillation is 0. Right.
So the other question I wanted to ask about the added mass, what's h in that expression?
It is effective thickness of the swimmer because it's essentially density per unit per unit thickness of the swimmer, right? So we don't have really density of the solid because it's two-dimensional.
So what do you take for the...
So this is density per unit thickness, okay? So you can think about this is volume of your swimmer. You have total mass, right? And then you divide it by area. That will be this expression. Right, and mass is essentially mass of your points you have on the surface, and you have the area.
And this blue band, which is called root, it is fixed here somehow.
Okay, so the condition we use at the root is essentially it moves up and down. It cannot rotate, right? So it's clamped in a sense, right? It can move, yeah. In this direction, it can move. Okay. We need to be on time for lunch, so. I'll better move on. So this is the what happens to the swimmer when swim. This is resonance frequency, aspect ratio 2.5. These beautiful colors show vorticity that is produced by the swimmer. So what we can see essentially, a swimmer swims. This is free swimming again. It generates vortices along the sides of the swimmer that shed it, and there is also vortex at the trailing edge. Almost nothing happens in the leading edge because we move it pretty much all the time in direction of the flow. Yeah.
Did you also try rounder edges because you have pretty sharp ends?
There are endless number of options, of course. We try to be like as simple as possible. Okay. Yes, you can. If you look at the fish, they never rectangular shape, right? So probably a reason for it.
Might cause some vortices at these sharp edges.
Yes, yes.
Is that sort of ladder of red stripes which appears every beat? Is that something to do with the lattice, or
it is just how MATLAB generates vorticity, calculate vorticity, because we still on the lattice, right? So it's just not really smooth. It's a little bit artificial because you need to calculate vorticity at each point, right? So and your velocity is discrete.
So it's a lattice artifact.
It's kind of artifact of visualization.
Computational lattice.
It's visualization artifact in a sense. Okay. So this is the thing. So we generate these vortices, and what you see here, we're at resonance, right? So the swimmer essentially interact with the vortices as shedded, right? So that's why you have this kind of relatively complicated structure because it goes through the vortice, which is actually not very good. Okay. So now we can quantify this process, and what we measure is essentially free swim velocity, which is shown here. So this is the velocity. We normalize it by the characteristic velocity of the swimmer. So essentially 1 would mean that for one oscillation, it moves 1 body length, right? And we see it's relatively fast. So this is reduced frequency. So 1 is resonance. In fact, 1.1 is resonance for the swimmer because when it moves, the resonance frequency a little bit shifts, right? So this is real resonance frequency is 1.1, and it moves relatively fast. It's 1.6 times of body length, right? So for one oscillation, so it oscillates and moves relatively far. Another very interesting feature. So it always happens for any added mass. It happens at the same frequency, right? It does increase when we use heavier swimmer. So you can think about, okay, you have heavier swimmer, so you have larger displacement, and then we can create faster swimming. That's pretty much what happens in this story. However, if we go for larger frequency, and this is this number 1.7, it's a magic number. I will show you in a couple of slides why. Then we have essentially flip of this behavior. So now, if we go to this frequency, which is shown by these green points here, the velocity increases for lighter swimmer. So if we have swimmer that has lower mass, it can swim faster, and this is versus what happens at resonance when heavier swimmer wins. Okay. We need some power to drive the swimmer. And if we measure the power, we see something really not good, actually, because what we see is that power grows pretty much exponentially when we increase mass of the swimmer. So it's really a sharp increase if we go to heavy swimmers. So 0.5 is the heaviest we tested here. And you can see that essentially difference in velocity between these two swimmers, maybe 50%. Change in power is pretty much more than 1.5 order of magnitude, right? It's like 20 times or something like that. So it is a really dramatic change when we increase the mass of the swimmer. But of course, this is, again, we see that happens at resonance. So you can already think about what happens to efficiency, and we can easily introduce efficiency, which is the ratio of the velocity the swimmer swims to the power we spend to activate the swimmer. So essentially tell us how far we can move per unit work, right? And that's what's shown here. So this is performance. It's not efficiency, it's performance. Efficiency is not very clear what's efficient for the swimmer. But what we see now that at resonance, actually performance is not that good. Especially for heavy swimmers, it's actually minimum. So you don't want to swim at resonance. If you want to be efficient, you can swim fast, but you will spend a lot of energy to do this. Interesting enough, there's another regime, which is this 1.7 I told you before, which we have maximum. And this maximum move is for all swimmers for added mass. We test it, and here we see essentially that our light swimmer is always wins. It actually wins for all range of frequencies we have. So light swimmer is always more efficient, and the maximum is in this point. Okay, there's also kind of interesting effect. So if you continue to increase the added mass, so you use lighter swimmer, you don't have any advantage anymore, because you can see it's kind of saturates, right? So this scale is actually wrong. It should be multiplied by 2.5. Okay, but it is saturating. So what I want to do, I want to compare these two regimes and try to understand why one is efficient and another one is fast. So what we have here is the animation. Again, we show the vorticity for these two cases. This is maximum velocity. This is heavy swimmer. What we see, well, this generate these vortices, but eventually it's a mess, right? So you generate these vortices, and then it goes through the vortices. Interesting thing, if you look at this, it does not move uniformly forward. So we use a reference frame which moves with the velocity of average velocity of the swimmer. So we can see that swimmer all the time goes faster and slower, right? So you can think about this is already not efficient. It's like you drive your car, instead of driving with a steady velocity, you all the time accelerate and brakes, right? So this is something that reduces the efficiency of the swimmer, but you have this huge deflection of the swimmer that essentially help us to propel forward. In contrast, if we look at this high performance regime, what we see is very well organized structures, these toroidal structures that the swimmer sheds, and it's actually, it pretty much not really interacts with these structures, so it's managed to go around, right? So it does not spend energy to interact with this structure that makes this more efficient. So we use a Reynolds number 80, but it's defined on length of the swimmer, right? Length and frequency. So I mean, it depends. If you take like amplitude of oscillation, it will be something else, right? I don't know what's the best for this. So here, what I want to show essentially is the deflection of the swimmer over one period, and we started here. So different colors show different quarters of the cycle, and then it goes up, goes down, goes up again, and this is the end of the period, right? So what happens for this fast swimmer, it actually, part of the cycle the deflection is so large it actually moves against the flow, and that slows down the swimmer, right? But then it accelerates again when they push fluid back, and then it accelerates, right? So these give us this oscillatory motion, which is not very efficient. But if you look at this picture, when we essentially plotted all these profiles to the same position at the root, we can see it's indeed the first resonance. So the phase shift between root and trailing edge is 90 degrees, so it is indeed the resonance. If we look at high performance regime, we see something different. First of all, we see that kind of envelope of this oscillation is relatively small, right? The second thing is, if we overlap all these snapshots, we see it essentially move in a mode where we have sort of line around which the swimmer rotates. So instead of, it essentially moves in this kind of mode. So it rotates all the time, back and forth. So why is it good? So what we can see in this case is essentially, okay, so if we look back in this story, in this fast swimmer, so if it moves up, it needs to move all the fluid around the swimmer, right? The fluid is incompressible, it cannot do anything with it, it should go somewhere. So it moves up, it pushes all this fluid around the swimmer. In this case, however, what happens, it can move the swim, it has a part of the stroke when it moves up and down, right? Part of the body, sorry, is moving up, part moving down. So essentially, it moves the fluid along the swimmer back and forth. So it oscillates like that and push the fluid back and forth. It don't need to go around the swimmer, so it seems to be much more efficient. And indeed, if we look at the forces on the swimmer, so as you mentioned, indeed, we total force is 0, but very period, but we have force that oscillates, right? And this is the force in vertical direction. This is the force in horizontal direction. So this is instantaneous force, how it changes. And these two lines actually show the forces on a high performance regime swimmer, and they are almost 0 compared to what we see in the fast swimmer. So we see that at high performance regime, we have very, very, very low forces, which essentially tells that swimmer has condition that forces all the time balance it essentially in time. So not over a period, but also instantaneous forces are very low, and that means there's relatively small acceleration of the fluid, so which make the swimming efficient. So let me go for a second back. So I put this figure here. Also, it's kind of a little bit provocative. So this kind of resemble what we have here. This one resembles what we have here. Also, Reynolds number for these guys is way, way larger than what we use in the simulations, but there may be some sort of analogy between the cases. Okay. Okay, I still have time before the lunch, right? My gosh. Okay, we'll move even faster than swimmers. So we can also introduce another parameter if we want to compare performance of the swimmer. We can, for example, compare it with power we need to pull a plate for the fluid, right? So this is maybe the most efficient way of transporting something for the fluid. We just take a plate and pull it through. So we can compare it with the power that is required to oscillate the swimmer, and this is the ratio is plotted here. So interesting enough, we find that, again, light swimmers are better, but the optimum performance neither at resonance nor at the regime we saw before. So it is because the power required to drag the plate is not linear with velocity. And we also see that actually the optimum changes with frequency. So if we use this metric, so this is how it changes. It can be sub-resonance, over-resonance, and over-resonance depending on the added mass. Okay. One more thing about this passive swimmer, I want to show you what happens if we change aspect ratio of the swimmer, right? It turns out that if you use a swimmer which is wider, then you have a faster velocity. So that makes sense because fish use usually fin that are wider if it is fast fish, right? So it does help to swim faster, right? And that's what we see here. But essentially, it saturates if we go to, this is 1 over aspect ratio, if we go to maybe 0.7 aspect ratio, so it's like 70% length over width of the swimmer, so there's pretty much no benefit anymore. Okay, we can also look for this case for power, a little bit larger power, but overall performance is better for wider swimmers. Also, the benefit is not very significant. Okay, so let me, 5 minutes, talk about active swimmers. So to model these active swimmers, we change very little the model we use. Essentially, what we do, we introduce equilibrium angle for our bending springs that changes in time according to sinus, and this is essentially mimics the internal moment we have in the system, right? So to keep it swim, right, we also fix the angle at the root of the swimmer, so it can move horizontally, but there's a clamp condition at the root of the swimmer, because if we don't do this, everything will be symmetrical, will just stay at place. And we can compare it with, say, theory. This is in the experiments with this MFC. So this is in air, this is underwater. It's kind of matches very nicely. Also, we use very simple model because the real material is very nonlinear, but for our purposes right now, it's good. So these are two cases. So this is our passive swimmer we saw before. This is active swimmer, so we clamp this part, but it can move forward, of course, and then it is actuated by internal moment, which actually tries to keep the curvature constant along the swimmer. That's what it does, right? So it's kind of uniformly distributed moment on the beam, essentially. And the question is, which one swims better? So how to compare them to these two cases? What we do, well, maybe it's not the best way to do this, but we essentially match power that the swimmer consumes at resonance, right? So effectively, power will change, but we match it just in one point and try to compare these two guys. Okay, here it is. So if before that was kind of messy structures, now we have something even more complicated, and the reason for it is because we have internal moment, this swimmer at least tries to align with the velocity. So then this trailing edge produces some vorticity, but it's kind of small. This one does not try to do this because it's always bent by this internal moment, and it's managed to generate even more vorticity compared to our passive swimmer. Okay, so at least in this point of view, active swimmer is better. But if we look at the thrust, so essentially we keep the swimmer constant in constant position and measure the force that it generates, we see that our passive swimmer is better, pretty much 50% fast, better than active swimmer. If we go further and look at the swimming velocity, okay, so this is passive swimmer and this is the active swimmer. It swims half slower at resonance, so it is not good swimmer in terms of its velocity. We think about how we can improve it, because essentially the problem is that we have this trailing edge that all the time tries to go through the vortices and reduce the performance. So what we can do some hybrid swimmer which has active and passive part, and then this passive part may help us to deal with flow structures near the swimmer. And indeed what we see, this is when we have 1/3 of the swimmer active, 2/3 passive. This is when we have 2/3 active and 1/3 passive. It does help with velocity, and essentially that's what we see for the fish. So it has active body which bends, and then we have some passive fin that's sitting at the end, right? So this is, in a sense, goes in that direction. We can look at also at the performance of the swimmer, and well, performance is bad. Okay, so we have it. It's actually this is kind of part we try to understand now, but it does not look good. For all these cases, it's several times lower performance that we see for passive swimmer. But if we go to low frequency, then actually active swimmer is not that bad, but they swim slow. So this is an animation showing the active swimmer at the regime when the frequency is low, and we see that it forms this kind of toroidal structures we saw with this high performance regime. So it seems like this is the reason it can gain some efficiency for low frequencies. But overall, not that good, but we have some hope to improve it by combining this passive and active part. Okay, that's my summary. Well, I have another summary. So, so first of all, we looked at the passive swimmer, and this one we kind of understand how it works, right? So if we want to swim fast, probably resonance is good. If we want to swim efficiently, it is not good, right? We need to go to a different regime, which is essentially in between first and second resonance in a sense. But this efficient regime essentially helps the swimmer to align with the flow, so it is producing less kind of parasitic currents in the flow, which reduce the take power and reduce the efficiency. Now, if we talk about active versus passive swimmer, so what we see now is that, well, passive swimmers swim faster, produce higher thrust, and have better performance, right? Active swimmer, on the other hand, manage to consume more power, right? So it is better at low frequencies, but that's the only benefit we see right now. But of course, there is some ways to improve it, combined with active-passive parts. That's actually experiment we try to build. So this is active swimmer, and this is passive tail. Or we can also, because this active material, we can combine two parts that actuate at, say, different phase. This is also possible. There are many options. Because the material is active, we can actuate it in very sophisticated ways and improve the swimming performance. Yeah, so, but this is for the future work for the student. Okay. Thank you for your attention. I still have 2 minutes to answer you. 1 minute.
All right, so I think since Alex went through at such a pace so that he could leave some time for questions, we should have some.
For lunch.
I didn't find your discussion of forces and efficiency very convincing, because I visualized your bending plate more as the tail of a fish, and then you've got the body to deal with. So the body exerts most of the drag, so your force balance between thrust and drag is not sort of very well represented by these calculations. This looks like, as I say, a good model for the tail of fishes which activate their tail and not much else, like the fast swimmers. Would you like to comment?
Okay, so that's correct. Essentially, again, we try to simplify our problem as much as possible, right? So if you attach it to the fish, right? So essentially what you will have is, well, you may have some hydrodynamic fluid to the body, but you will also not swim in free swim, because your drag force will be larger, you will swim slower, right? But again, so the idea here is to understand the simplest possible case, because we don't really understand it well, right? So yeah, we can definitely change. We see that if we change the velocity it swims, so yeah, but with structures that's very similar still, right? For active swimmer, essentially, it is actuated, the body itself is actuated, right? So again, you may think about some external body that attach in the front that keep the swimmer from essentially rotating, right? But we try to simplify it. This is the only reason to, yeah, it's kind of spherical cow, you know, so.
Yeah.
This equilibrium that you're perturbing by, it's with respect to the system you're looking at, where there is this constraint. That's basically the system you're looking at. There's these constraints that are externally imposed.
So essentially, we impose the boundary condition at the root, right? Those are the only constraints. So for the passive swimmer, it's displacement and rotation, so we not allow it to rotate at the root. For active swimmer, it's just rotation, so we not allow it to rotate. That's the only constraints we impose.
You did cite a paper, and it says like which equilibrium is being looked at, and it's definitely this one. This one that you're analyzing in this talk?
We didn't publish it, so.
Okay, yeah.
In some related systems, you'll see that these vortices or vortex dipoles that are shedding from the trailing edge end up, there's a symmetry breaking in the fluid, right? So in this case, that would be associated with some kind of lift or something, which I would imagine would be problematic for a fish. It'd be constantly turning or something like that.
Well,
Do you see some, in some regime of,
Well, we didn't look at this story leaf. We didn't search for leaf because for fish it's kind of useless. But we actually looked at different little bit. Sorry, when we look at essentially like
I just mean
vertical force. Yeah, I understand. Yeah, I mean the force in this direction, right? So we looked at a little bit different system when we had like two wings that attached in an angle and then you oscillate it. Right. We also see this kind of two regimes, although they were completely different frequencies. But there's some analogy with flapping hydrodynamics too, right? So you have resonance and.
But so in the regime that might be relevant for fish locomotion is that kind of, do you see appreciable lateral forces? I didn't quite catch.
We don't see any lateral force here because it's everything is balanced. I mean, it's zero always. What do you mean by lateral forcing?
Well, I mean, you can have symmetry breaking in the fluid, which will lead to lateral.
Well, we impose the bar. We don't have it.
Okay.
Oh, you mean is it stable or not? If it tries to swim aside as.
Even with symmetric lateral motions of the fin, even if the kinematics are prescribed and symmetric, you can still have symmetry breaking in the fluid, which will lead to, through vertical interactions.
No, what we saw is pretty much symmetrical.
Okay.
So we didn't see any difference between, yeah.
I hate to cut this off, but to give everybody the opportunity to choose between lunch and asking more questions, let's end the formal question period right here. And thanks, Alex, again.
Thank you very much.